All right. This is another example of motion with rolling and slipping. There's a ground and there is a ball. And this ball is given an initial condition. It is moving with velocity v0 and its angular velocity is 0. For example, this could be a ball you throw when you play bowling, or this could be a ball you hit with a stick right in the direction of its central mass in the billiard game, billiard ball. And there is a coefficient of kinetic friction between the ball and the ground. It is mu. And of course, ball is moving, but there is friction. And at some point here, when the velocity is vf, now it is rotating with omega f, and at this point, from this point on, it is rolling without slipping. So we are given the mass of the ball, m, and the IO is 25 mr squared. This is solid sphere. All right. And, well, let's say given mr IO, which is 25 mr squared, and V0 and mu, omega 0 is 0. Let's give that also omega 0 is 0. Find, well, rolling without slipping means Vf is equal to omega fr. So Vf omega fr. So if you find one, the other one is easy. But here they are not related with such a relation because it is slipping and rolling here. And let's say if this distance is d, what is the distance d? And when does it, if this is the time equals 0, what is the time here when it starts rolling without slipping? So let's call it time t. Okay. And then, of course, there are a host of other questions you can ask. For example, we can ask about the translational energy, the rotational energy, and, for example, how they are changing with the position. At this position, for example, what is the translational kinetic energy? What's the rotational kinetic energy? So these are the questions we want to find out. Before this one, some time ago, in this series, I solved this problem so that you can compare. There was a cylinder. It could have been a sphere. I took a cylinder then. It was rotating with omega 0, and its velocity v0 was 0. It was dropped on a surface, and after some time, again, it's going with vf and omega f. So we will solve this problem, but it is instructive to compare the results of this with the results of that. Okay, this is already in the playlist of the problem solved. I'm erasing it, or let it stay for a while. This is a previous problem. Previous problem solved. This one is solved. Okay, so we will solve this one. Before we do anything, let me just look at the dimensions. What are the distances and the times involved in this problem? Well, there is the friction force, and the friction force will be F equals mu times mg, or m times mu g. So the acceleration is characterized not by g because it's not falling, etc., but it is really mu g is the acceleration. And we have a given velocity v0 and energy E0, which is the k translational initial, that's 1/2 mv0 square. So this sets the energy scale, all the energies, the work done by the friction, how much energy is eaten, etc. We will compare it with the E0. Okay. Time. So time parameter here, time. V0 is distance over length. So it goes as V0 over mu g. It could be 5 or 3 or 1, 2. This coefficient, of course, will be determined by the dynamics of the problem. But it will be something times mu g. This is length over time squared. This is length over time. So time flips over. But it is some coefficient times this. And finding the coefficient means solving the equations. That's not... And d, that's distance. So it will be v0 square over mu g, because this is L square over T squared. This is L over T squared. T squares cancel. As I'm looking at the dimension. So dimension is length L. Likewise here, L over T divided by L over T squared. So this is just T. Okay, so this distance is some coefficient which will times V0 square over mu g, and T will be in terms of V0 over mu g. All right. And so these are the characteristic times and lengths. This is the characteristic energy. Now we can write the equations of motion. First, the translational motion. So let's take the position of this thing somewhere here. Okay. I'm isolating the body. Here there is the friction. That's the only horizontal, since the body is not jumping up or going down the ground. It's only moving in the x direction, let's say, horizontal direction, and the only force acting on it is F. And therefore, the velocity, it's accelerating to the left, namely its acceleration is reducing the velocity. Therefore, V of t is equal to V0 minus acceleration times t. Acceleration is mu g times t. All right. And how about the angular rotational motion? F is giving a torque. So F times R is IO alpha. I'm taking the torque about the central mass of the disk. Sorry, central mass of the sphere, of the ball. So mu mg r is equal to 2 over 5 m r square alpha. M's cancel. So alpha r is 5 over 2 mu g, or 5 over 2 a. That's alpha r. So omega t is omega 0. Now we have to take a positive direction. If it's rotating this way into the blackboard, and we take it as a plus. So omega t is simply alpha t, or I can write omega 0 plus alpha t, but omega 0 is 0. That's simply alpha t, and alpha is 5 over 2 a over r, a is constant, times t. Or let me write omega t times r is 5 over 2 a, which is mu g t. So this is the equation governing the translational motion. This is the dynamical equation, or the velocity equation for the rotational motion. So this is the rotational speed, this is the translational speed. Okay, this goes from 0 to time t. Time t is here. This is the time when it begins to roll without slipping. So omega f t, that's equal to v0 minus mu g t, and omega t r is equal to 5 over 2 mu g t. But these things are equal. Omega f t is equal to omega f t times r. Why? Because at that point, rolling without slipping sets in. Therefore, we equate the right-hand parts. So v0 minus mu g t, that's equal to 5 over 2 mu g t. Or v0 is, this is 2 over 2, 7 over 2 mu g t. So we found this time t. T is equal to 2 over 7 mu g. v0 over mu g. Let me write here. This was the previous problem. One should compare with this problem. That one. All right, so we found t is 2 over 7 v0 over mu g. You see, just from the dimensional analysis, we got v0 over mu g, but 2 over 7 requires all of that. Okay. So to find vf, we now know t, so we just put in. I'm erasing, or I can do it here. Vf t is equal to v0 minus mu g times t. T is 2 over 7 v0 over mu g. So 7 over 7 minus 2 over 7, that's 5 over 7 v0. So we found vf is equal to 5 over 7 v0, and omega f is vf over r, or 5 over 7 v0 over r. So we found the final velocity, we found the time, and now we'll find d, and I'm erasing all these. Let us now try to find d. Friction is eating up the translational kinetic energy. So the negative work done by friction is minus mu mg times d. Namely, this is F minus F times d. This is equal to K translational final minus K translational initial. This is E0. This is 1/2 m Vf square minus E0. Vf is 5/7. So it is 1/2 m. 5/7 square is 25/49. V0 square minus E0. 1/2 V0 square is E0. So it is minus E0. 1 minus 25/49. 24/49. E0. So minus mu mg d, that's equal to minus E0 24/49. In other words, W minus friction, namely, I'm saying minus, it's eating up the energy. Then divide by E0 is minus 24/49. So almost eats up the half of the initial kinetic energy. Now to find d, minuses cancel. Mu mg d is equal to 1/2 m V0 square times 24/49. M cancels. D is in terms of V0 square over mu g. So d is equal to 24 divided by 12/49 V0 square over mu g. So let me write here d equals 12/49 V0 square over mu g. There is another way of finding d by using this formula. X equals x0 plus V0t plus 1/2 at square. And here d is equal to, it starts from 0, x0 is 0, V0 is given. Time is now this t, where is it? This t. Acceleration is negative. We are going this way, but the acceleration is that way. 1/2. Acceleration is mu g t square. T is 4/49. V0 square over mu g square. V0, 2 over 7 V0 over mu g minus 2 over 49 V0 square over mu g. Let me just pull it here. So I have V0 square over mu g, parenthesis, 2 over 7 minus 2 over 49 multiplied by 7. So this is 14. 14 minus 2 is 12. So it is 12 over 49 V0 square over mu g. So it's the same thing. Okay. So we found D. All right. It may be interesting to, so this is the distance it covers until rolling without slipping sets in. Notice that from this point on, there is no, since Vf is equal to omega Fr, the rotational and translational motion is in lockstep, namely there is no more friction force. It will continue with this velocity. And perhaps I should indicate that remember V of t was V0 minus mu g t, and omega t r was alpha RT so this is T over T. This is, let's say, 1. This T is that T. 2 over T, V0 over mu G. So this is V over V0. So translational, this is 1. All right, I erased those equations, but it's good to rewrite them. I have the D. Can erase it all. So V over V0 is equal to 1 minus mu G over V0 T. Let's measure T in terms of T. T over T times T. That's equal to 1 minus mu G over V0. T is 2 over 7 V0 over mu G. 2 over 7 V0 over mu G. This is, let's call T over T tau. So this is 1 over mu G over V0. This is T, 2 over 7 V0 over mu G times this tau. This is the scaled time. So these things cancel. So it is 1 minus 2 over 7 tau. This is V over V0. Remember, this V is the translational speed. V over V0 at tau equals 0, it starts, tau is the scaled time. Okay? When tau is 1, you are here. Time is equal to t. Tau is the scaled time. So it becomes 5 over 7. So let's say this is 5 over 7. So V comes like this, and then, of course, omega, to compare, we have to bring the dimensions the same, so it is that way, omega tr, if you wish, let's call it V rotational at t, that's equal to alpha r t, and again, fr is equal to 2 over 5 mr square alpha, r cancel. R alpha is, this is mu mg, m's cancel, so r alpha is 5 over 2 a, which is mu g. So it is 5 over 2 mu g. T again, t over t times t. This is just tau. So it is 5 over 2 mu g. This is 2 over 7 V0 over mu g times tau. Mu g is cancelled. So it is, as you would expect, it is 5 over 7 V0 tau. This is V rotational. So V rotation over V0 is simply 5 over 7 tau. So it starts from 0, goes to 5 over 7. 5 over 7 is here. So this is the V translation, this is the V rotation, if you wish. All right. We found D. Okay. This is an interesting graph about the velocities. No rotational speed at the beginning, it's picking up, and this is losing speed at this time. Rolling without slipping, and friction stops, and it's moving with constant speed and with constant rotational speed. I'm erasing all this. I want to show this graph. Okay, this is gone. This is also interesting in the sense that we measure time in terms of this t. It sets a time scale. So this is also gone. Now I am looking at the how the E translational at x, how does it change with x from 0 to d? So this is E translational initial, which is 1/2 mv0 square, which we call E0. That's equal to minus mu mg x. But x we can scale with d, so it is minus mu mg x over d times d. Let's call eta is equal to x over d. So eta varies between 0 and 1. So it is minus mu mgd. That's equal to times eta minus mu mg. D we found, that's 12 over 49. 12 over 49 v0 square over mu g eta. So mu g cancels. And let me write as minus, I divide by 2, multiply by 2, minus 24 over 49 E0 eta. So that E translational at x divided by E0, I take this one to the right hand side, becomes, this is minus E0 becomes minus E0 becomes plus E0. So I take to the E0 divide. So it is 1 minus 24 over 49 eta. So if you plot here E translational over E0, this is eta, which is x over d. So this is 1. It starts totally in the kinetic mode, and when eta is 1, it goes to 25 over 49 when eta is equal to 1. So 25 over 49 is like 1/2. So it is 1/2. It is slightly, okay. So the velocity is dropping, translational mode is losing energy in this way, and friction is doing negative work and eating up the energy of the translational motion and reduces it down to 25 over 49. So this is the E final translation. Okay, it starts from 1, and in time capital T reaches eta equals 1, or the position D, and this is the final translational kinetic energy, which is about half the initial. Okay, let's look at the rotational kinetic energy now. Now I'm considering only the rotational mode, F, and rotating this way, we took it as plus. Now initially it was not rotating, and friction is forcing this rotation. Okay, Fr is tau, and namely the torque about the point O, and tau d theta is the omega plus friction. Namely, it's the elementary work done, which is positive by friction. So friction is doing negative work to reduce the translational motion, but it is doing positive work to increase the rotational motion. So Fr theta is omega plus friction, and we know what this is. This is 1/2 IO omega F square minus 1/2 IO omega 0 square. Omega 0 was 0, so this is 0. So we know what this is. 1/2 2 over 5 m r square, and omega f, we found it here, 5 over 7 square it, 25 over 49, 25 over 49, V0 square over R square. So 1/2 m V0 square is the initial energy. So it is E0 times, how about here, 5, R square cancels, E0 times, 2 times 5 is 10, 10 over 49. 10 over 49. So 49 is like 50, so it is 1/5 of the initial energy. So in translational motion, half the energy is lost by friction, but friction adds 20%, 10 over 10 over 50 to the rotational motion. And let's look at R theta. So R theta is equal to 5 over 49, 5 over 49 V0 square over mu G. Let us compare it to D. So it is 5 over 12 D. So it is less than D. So what does it say? It says that if you take a point here, when it was just beginning its motion with the speed V0, this P rotated by so much theta, and if you multiply by R, it is less than D. So this is obvious because part of the time it was sliding. So R theta we expect to be less than D, but now we know it exactly how much less. Okay, it is less than half of D. In the other problem, if you remember, when we put the object with rotating this way, and when the Vf and omega f rolling without slipping condition was satisfied, here in the previous problem, R theta was larger than D. Here it is less than D. Okay. Can we, one last thing, can we, I erased it, but I sort of remember, I hope it's correct, E translation over X or eta over E0 was 1 minus 24 over 49 eta. Eta being X over D. I will erase this part now. All right. One last item. E rotation at X. So from 0 to d, it comes at d, it is 20% of the initial energy E0, rotational energy. But how does it change with x? Can we do that? Okay. So it is 1/2 IO omega t square The question is, we must relate t to x, t of x. Can we find t of x? Because this is simply alpha squared t square. So if we find t of x, then we plug it in and we will find this rotational energy at the, at the position x. Just the way we found the translational energy as a position of x, or scale distance x over d. So we need to find t of x. How is x related to t? So x equals x0, which is 0, plus v0t minus 1/2 acceleration. Acceleration is minus mu g times t squared. So we have to solve this quadratic equation. So we multiply by 2, okay, divide by mu g, and the equation we need to solve is this, 2 minus 2v0 over mu g plus 2x over mu g, that's equal to 0. That's a quadratic equation, has 2 roots. T12 is equal to v0 over mu g plus or minus root v0 over mu g square minus 2 over mu g x. I multiply by d, divide by d. X over d is eta, and I insert d. So this is equal to v0 over mu g plus minus root v0 over mu g square minus 2 mu g. X over d is eta, and I write d. d is 12 over 49, 12 over 49, v0 square over mu g, v0 square over mu g times eta. So t, so this is v0 square over mu g square. v0 square over mu g square, so it goes away. T is equal to t over v0 over mu g is 1 plus or minus square root of 1 minus 24 over 49, 24 over 49 eta. Now there are 2 roots. Which one? Eta goes from 0 to 1. Which root? Eta goes from 0 to 1. So when eta is equal to 0, we are here. Remember, eta is x over d. Eta is x over d. And when x equals 0, time is 0. We are here. So if you put eta equals 0, we either have 2 or we have 0. So we must take the 0, the one that gives 0, that's the minus. So we found t of x. Let me write here, t of x is equal to T of x over V0 over mu g. Okay. That's equal to 1 minus square root of 1 minus 24 over 49 eta. That's our T of x. I am erasing this now. Okay, so we are here. So 1/2 2 over 5 m r square alpha square. What was alpha? We didn't write it, so we have to find it again. Fr is equal to IO alpha, and mu mgr is equal to 2 over 5 mr square alpha. M's cancel. Alpha r is equal to 5 over 2 mu g. Mr square times alpha square times t square is that square. So V0 square over mu g square 1 minus root this thing squared. So this gives what? 1/2 m V0 square is E0 then I have 2/5 r square alpha r, which is 25 over 4 mu g square. What did I write? I wrote alpha r square times V0 square. No, V0 square is gone. Mu g square is here. Mu g square 1 minus root square. So it is 1, 5, 1, 2. Mu g squares cancelled. So E rotation at x divided by E0 is 5 over 2, 1 minus this root thing square. So I will take the square. Let me write it completely. 1 minus 24 over 49 eta square. Square is only on the parenthesis. So I am erasing these. E rotation x divided by E0 is equal to 5 over 2 times 1 plus 1 minus 24 over 49 eta, the square of this plus the square of that, minus 2 square root 1 minus 24 over 49 eta. So this is 2. So this is equal to 5 times 1 minus 12 over 49 eta minus root 1 minus 24 over 49 eta. Let's check for eta equals 1. Eta equals 1. Remember, eta is x over d. When eta is 1, we are here. And we know it should be 10 over 49. Let's see. E rotation. This is now a function of eta. Eta equals 1 over E0 is equal to 5. 1 minus 12 over 49. This is 1, so it is 25 over 49, so it is 5 over 7 minus 5 over 7. Which is 5, 49, 5 over 49, 49. Minus 12 minus 35. So this is 47 minus 47. So this is 2, 5 over 49 times 2, which is 10 over 49. That checks. So we got the result. We knew from before that at this point it is 20% of the initial energy. So let's check, for example, E rotational eta very much smaller than 1 over E0. You see, the scaling helps in this way. When eta smaller than 1 means x is very much smaller than d, when you are just at the beginning. So we'll just expand 5, 1 minus 12 over 49 eta minus so this is 1 minus 12 over 49 eta, etc. So you see, in the linear scale they are cancelling, so it is eta square. Namely, it starts slowly going up. So this is eta, this is 1, this is E rotational over E0. This is, of course, function of eta. All right. So at most it will go to 10 over 49. So let's say this is 10 over 49. So it is coming up slowly and then picking up speed. All right, so that's it. E rotational x divided by E0. Finally, let's add them all up. So this is when rolling without slipping sets in, and this is when at the beginning of the motion, just around here, I am racing. So that's the exact formula. So let's wrap it up with the energies. E translational x over E0 was 1 minus 24 over 49 eta. And if you add them up, E total over E0 is equal to so we have 5 plus 1, there is 6. This is 60, 84 minus 84 over 49 eta minus 5, 1 minus 24 over 49 eta. So this is the total energy when eta equals 0. When eta is equal to 0, this is 0. This is 0. We have 5. 6 minus 5, 1. So E total over E0 is equal to 1 when eta. So E total over E0 eta equals 1 is equal to 1. Namely, your total energy is E0. Sorry, when it is 0. At the point where it sets in, E total over E0, eta equals 1 is equal to 6 minus, well, this thing actually simplifies by 7. 7, and this is 12. Minus 12 over 7, and this is 1. 49 minus 24 is 25. Square root is 5. 5 times 5, 25. Minus 25 over 7. So it is 6 minus 37 over 7, or 42 minus 37 over 7. So it is 5 over 7, or 35 over 49. This is E total over E0. And so this 35 over 49 we can understand like this. Where shall I erase? All right. This is rotational. This is the total. Okay. We start with E0. In the translational mode, from E0 it goes down to 25 over 49. I give 1 to 25 over 49 E0. Okay. In the rotational case, energy starts from 0, goes to 10 over 49 E0, and the total is E in the translational mode plus the rotational mode, so 25 plus 10 over 49 E0, which is 35 over 49, or 5 over 7 E0. Okay. So this is the E rotation E. So roughly speaking, the total, I can erase this part. So if you look at the E total over E0, and this is eta equals 1 here. This will start from 1. It will go down to 5/7. So it is perhaps somewhere here. Here it will remain constant. It will first go down linearly and then taper off like this, or something like that. Okay. So translational mode energy goes down linearly. Rotational motion energy goes like this, starts very slowly and then picks up. And this is the total energy that goes to 5 over 7. Okay, I think we understood all the things that's going on in this problem. Namely, we found v velocity, we found the angular velocity, when the rolling without slipping sets in, where the rolling without slipping sets in. We found the change in the translational energy, in the translational mode, the energy of the translational mode. Where is it? It is here. Okay. And we found as a function of eta, or as a function of x. And we found the change in the rotational, the way it increases in the rotational mode, it is that, and how the total energy decreases as a function of x. That settles everything about this problem. Please compare it to the problem we solved previously. I repeat again, compare this one with this, namely that it was rotating with omega 0, there was no velocity, and then it is rotating with omega f and vf. So if you just compare these two problems, they are solved in the same way, but starting with different initial conditions. Thank you.